Working with 1.2, which is on converting decimals, which you've done in 6th and 7th grade. We'll take it a little bit farther. And then we're also going to be looking at the real number system, which you guys did rational versus irrational last year. We're going to be doing the same thing, just taking a little bit deeper into sorting it into more specific categories. So the first thing we're going to look at is when we convert a terminating decimal. So in this case, a terminating decimal, if you terminate somebody, if you're an employee and you're terminated, it means your employment there has ended. So this is an ending, a decimal that comes to an end. That's one of our vocabulary words. So this one comes to an end because you see that it's 1.65. We don't have bar notation, which you guys learned about last year, meaning it repeats, and we don't have the ... after, which means that it just keeps going and going and going. So if you have just a decimal number like we have, 1.65, you're going to put it right in our calculator, and then above the enter button is our conversion key that looks like this, and we're going to push that. So we would put in, mine still might be up because I just did it on here, 1.65, and then you're going to hit your conversion key above enter. This calculator is the same as yours. It looks a tiny bit different because I'm putting long ways instead of up and down. So it came out as 33 over 20. So then you would just put 33 over 20. You don't need to convert it to a mixed number. You can just leave it just like that. So if we wanted to, let's try like 2.836. So again, we're going to put it in our calculator, and then we're going to hit our conversion key. Whoops, that's not what I meant to do. So if you do that, not that, but let's do 2.836 just as another example. So you should put it in your calculator, 2.836, and then mine does it automatically as I go. I would hit my conversion key right there, and it comes out as 709 over 250. So this one would be 709 over 250, and you'd be done. That's all you have to do on those. All right, so this next one is when we have what's called a repeating decimal. So repeating decimals are sometimes mistaken for non-terminating decimals. You'll notice that this has the ... right there. That means that this keeps going and going and going. Just because it says ... doesn't mean that it's repeating. The ... means that it keeps going and going and going. On this one, you guys learned it this way last year. So you put a bar over what repeats. So in this case, this bar is over both the 4 and the 5, which means this decimal would go 4, 5, 4, 5, 4, 5, 4, 5. And that's exactly what it's showing here. So like in your calculator, it will not give you bar notation. It will give you 4, 5, 4, 5, 4, 5, 4, 5, 4, 5. And so the ... just means that that same pattern is going to keep going. So a couple things that I want you to look at. I want you to put in your calculator 1 over 3, or 1 divided by 3. We're going to look for a pattern here. So I'm going to do 1 divided by 3, and I get out, you'll notice, 0.333333333. Now let's do let's do 3 divided by 9. And you'll notice that 3 divided by 9, sorry, I must hit something else there, comes out as 0.33333333333. And so 3/9, all 3/9 is the bigger version of 1/3. So we simplified it to get to 1/3. Now I want you to put 4 over 9. So in other words, 4 divided by 9. I'm just going to show you a few, and I want you to start to see if you can look for a pattern there. So now let's do 5 divided by 9. Now I get all the time kids to say, Miss Walker, this one is not repeating, because you'll notice it goes 0.555, 555, 555, 6. This is still a repeating decimal. The reason it goes to a 6 here is because it runs out of room on your calculator screen. And so if it can round up this last number right here, it's going to. You'll notice, I can go back on mine, this one didn't round because 4 is not going to round 4 up. This one didn't round because 3 is not going to round up. So now let's see what happens when we put in 6 over 9. So 6 divided by 9. Again, it repeats. The reason it has a 7 at the end is because it is going to round up. What happens when we put an 8 at the end? Sorry, an 8 divided by 9. Okay, so hopefully you're noticing a pattern. What did I have on the bottom of every single one of those? Now let's say that we get repeating like 12. So before we had one number repeating, like my 8 just keeps repeating here and it was over 19. What happens if I put 12 divided by 99? You'll notice I get out 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. What happens if I put in 15 divided by 99? We get out 1, 5, 1, 5, 1, 5, 1, 5, 1, 5. And again, it's going to round it up if it can. This is still a repeating decimal. So this trick will work as long as we have the same thing repeating. So like I said, right here, this dot, dot, dot just means that whatever it's doing is going to keep going, 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 going. So in this case, this is going to go 4, 5, 4, 5, 4, 5, 4, 5, 4, 5. The bar represents what's repeating. So this represents that it's going 4, 5, 4, 5. So in your calculator, you're going to push your fraction key. Our fraction key is the one that says n over d, and I'm pretty sure most of you have found that now. Then what you're going to do is you're going to put whatever repeats, the repeating number, on top. So in this case, our repeating number is going to be 45 because it repeats 4, 5, and then you'll notice that it goes 4, 5 again, and then 4, 5 again, and then 4, 5 again. So 45 is what is repeating. On the bottom, if we have 2 numbers on top, we needed 2 9s on bottom. So same amount of 9s on bottom. So in this case, we had 2 numbers on top, we need 2 9s on bottom. If this were going like 4, 5, 1, 4, 5, 1, 4, 5, 1, then we'd need 9, 9, 9. So the last thing we're gonna do is push enter. So we're gonna push the fraction key, put that in, and then we're gonna see if it simplifies. So I'm gonna just do it here. So we're gonna hit our fraction key. So n over d, mine's right there, and we're gonna put 45. And then over 99, and when you hit enter, it will simplify it. You'll notice that this simplifies to 5 over 11. So then I will come back over here, and I'm going to put that 4599 simplifies to, what was that, 5 over 11 again? Yeah, 5 over 11. Okay. So that's how we change those. So let's try another one. Let's say the number that repeats, they give us this. To show you that it repeats, I'll at least show you 2 sets of it. So when I read this, you're going to listen and see if you can figure out what I'm saying as a pattern of the same numbers. 5, 3, 2, 5, 3, 2. Hopefully you're saying, okay, it's 5, 3, and 2. So in my calculator, I would put 5, 3, 2. The number that repeats goes on top. On the bottom, since I have 3 numbers on top, I need 3 9s on bottom. And this one, I'm pretty sure doesn't simplify, so we'll just check though. We have 5, 3, 2. We have 5, 3, 2. Over 999. Now, if it comes out just like this one did, that means that this does not simplify. That's as low as that goes, is 532 over 999. So this would be done. All right, so you guys did those last year. Now what we're going to look at is when you have the real number system. So the difference between something that is rational. So rational are kind of like our pretty numbers. Any fraction will be rational. Any repeating decimals will be rational. So things that look like this. So square roots, what we were talking about yesterday, of perfect squares. So an example would be like if we had the square root of 25, if we put that in our calculator, we're going to get out 5. It comes out perfect. So no radical sign is left. So no radical sign or decimals. It comes out as a whole number. So that's the first thing we're going to look for. If it has a square root, it's either going to be a perfect square or a non-perfect square. Those are your only two options. Okay, now terminating decimals. These are decimals that end. So sometimes we look at something like this and we're like, but that's not a decimal. Just remember that this is the same as 2.0. So that ended. So instead of writing the 0.0, which doesn't matter, they just put it as 2. You might get something like 6.83. Again, it ends, it terminates, it comes to an end. You might have something like 0.214. It's going to end. You could have, if it's a fraction, it automatically comes to an end. So if they can write it as a fraction, it's going to be a terminating decimal. Just to show you, if we put in 5 over 8, so we put in 5 over 8, you'll notice I get out 0.625. It ended. It stopped right there. It didn't just keep going and going and going. So all of these are examples of rational numbers. They're the nice, pretty numbers because any of them could be written as, like I said, they're a fraction. So perfect squares, they come out as a whole number and only a whole number. Terminating decimals, meaning it comes to an end. And then we have our repeating decimals. And in our calculator, you might get out a repeating decimal that looks like this. And then it would end. So to show you that, they're going to show you like this. So this repeats, so you're looking at that going, if I said this out loud, 0.61616161, it could be rewritten as 0.61, both the 6 and the 1 are repeating, so you'd have a bar over it. You might have something that looks like this, 3.4555, and you'll get these in your calculator once in a while as well. Well, if you say 3.45555, what's the only thing that repeats there is my 5. So this would be 3.4. None of that repeats. My line or my bar notation only goes over that 5. So those are the 3 different things that are going to qualify them for rational numbers. Perfect squares. In other words, they come out as a whole number when we put in a radical sign. Terminating decimals, they come to an end. So it's a decimal that ends. And repeating decimals, which is a decimal that goes on forever, but like I said, you could put a line over what's repeating. The other option is irrational, and these are ones that do not make sense. They don't come to ends. They're these crazy numbers that keep going on forever. So these are non-perfect squares. So let's say that you put in the calculator radical 20. I'm going to show you right here. If you have your calculators, you'd be doing this too. So I'm going to put in radical 20. So second x squared, I put in 20. You'll notice right here, I come out with 2 root 5. 2 root 5. This did not come out as a whole number like we talked about here. This is why this is a non-perfect square. This is going to come out as 2 root 5. Which means this has a radical left, so it is a decimal that goes on forever and doesn't terminate, so it's a non-perfect. And you can see mine gives me both the root version and this version right here, which is a non-terminating decimal. You can see that it's like this totally random decimal that's huge number that has no pattern of the same repeating. So if I read this, I'd go 4.472135,955. We can see this is not repeating. So anytime you do it, if it's non-perfect, meaning it comes out at the radical, it is non-perfect square. So that makes it irrational because it didn't come out as that pretty whole number. Now these ones are the ones that tend to get the most mixed up. So sometimes, just like that one we had, you might get something that looks like this, negative 2.31689.4 ... When you read that, again, this ... does not mean that it repeats. It means that it keeps going and going and going. Well, in this case, there's nothing as a pattern. We don't have 316 repeating. It goes 316 and then it moves to a whole different number. So this is not a repeating or a terminating decimal. It's a decimal that goes on forever, does not repeat, does not terminate. The ones that are the most mixed up are these ones. Let's say you get something that looks like this. So 0.212112111 ... You could probably tell me what is going to happen next there. You could probably say, if based on what we're seeing, we would probably say that it's going to say 2 again and then 1, 1, 1, 1. This is not repeating. We can see a pattern, but if we were to use bar notation, where would that bar go? Because some kids will say, well, Miss Walker, just put it over the 2 and the 1. Well, if I only put it over the 2 and the 1, that means that my pattern should go 2, 1, 2, 1, 2, which it doesn't do that. So then some kids will say, well, maybe do 2, 1, 2, Mrs. Walker. Well, if I do 2, 1, 2, then it should go 2 again. So if you can't find where to place a bar, it is not repeating. And we know it's not terminating because it has the ... So those are the 3 things that we're looking at today. Well, I guess 4, because we're converting, which was one thing. And then you need to be able to tell if it's rational, so it fits into one of these 3 categories, or it's irrational and it fits into one of those 2 categories.